So diving right in, starting on chapter 4. So this is 4A. There's a very, I think it's a pretty short PowerPoint describing some definitions that we'll go over: molar mass, Avogadro's number, things like that. But for the most part, this chapter, the entire chapter, is just a lot of different calculations. So most of the information is going to come from the lecture, not necessarily the PowerPoints. So a little different than past chapters. So we're going to start by calculating molar mass of compounds. So molar mass is the same as molecular weight, same terms. When we're calculating these, the units are going to be grams per mole. And this will be more understandable when we use the convergence. But for now, just know once we finish these calculations, we're going to label the units as grams per mole. I know in the homework, they ask you to calculate the molar mass, the molecular weight, and then they have units of grams per mole. And then they also ask you to calculate the formula mass. Now, to calculate the formula mass, you do it the same way that we're about to do the molar mass. The only difference is the units. If they're asking for formula mass, the units are AMU. And what AMU is atomic mass units. That's what it stands for, atomic mass units. To be honest, it's a made-up unit. It's not really useful for much. The grams per mole units are going to be useful when we start doing conversions with it. So usually I'll ask you to calculate molar mass and use that term because the units I want you to report stuff in is grams per mole. All right, so how do we do this? It's actually very similar to when we calculated valence electrons when we were doing Lewis structures. We're going to take, for each element present in the molecular formula, in the chemical formula, we're going to take the number of atoms of each, which we get from the subscript, and multiply it, instead of by valence electrons, now we're going to multiply it by molar mass. So what is molar mass? How do you get it? How do you find it? Much like pretty much everything else, you get it from the periodic table. So let me get my periodic table. That is that average atomic mass that we talked about in chapter 2. So you're going to find the element in question on the periodic table, and it's the decimal point number underneath the chemical symbol. That is the molar mass of that particular element. So approaching a chemical formula, you're given the chemical formula, you're asked to solve for the molar mass, the molecular weight, the formula mass. No matter what they're asking you to solve for, we're doing it in the same way. The only difference is the units you put on it at the end. So I'm going to do it just like I did valence electrons. Make a list. I have calcium, I have chlorine. And then for each element that you have, you're going to take the number of atoms present in that chemical formula and multiply it by the molar mass. So for calcium, there is no subscript, so that means there's just one atom. So I'm going to take that one atom, multiply it by the molar mass, so when I find calcium, 40.08, and don't round, use all. So it's really helpful, the periodic table that I supplied for you, because they actually already rounded it. So you only ever have 2 decimal places, sometimes 3. And depending upon which periodic table you're using, you might have more. For instance, the one we have in class, some of the elements go out to 5 or 6 decimal places. All right, so if you use the one you have, just make sure you're using all the way out. Don't round it. Don't just say, oh, it's about 40. No, put 40.08. So now for chlorine, the number of atoms, we're looking once again at the subscript. So subscript of 2 tells me I have 2 chlorine atoms. Multiply it by its molar mass, 35.45. So you multiply across and then add them together. I don't know what that is, 78.90. Is that right? And then add. 110.98?
Yes.
Okay. And the units I'm going to put on it are grams per mole. If they're asking for formula mass, it's the same answer. It's just instead, your units are going to be A and U. That's the only difference. All right, let's try a few more. So now we have N2O3, so dinitrogen trioxide. Make a list. We got nitrogen, we got oxygen. Then atoms of each, molar mass of each. So we have 2 atoms of nitrogen from the subscript and 3 atoms of oxygen from the subscript. Nitrogen's 14.01, and then oxygen is 16.00. So yeah. 28.02, and I should know how to do that, but I don't. 48, thank you. Grams per mole. All right. So I'm going to have to erase this, I think, to do this one because it's a big one. So just a reminder for Sunday, Chapter 4A questions are due, and then the discussion as well. And that's going to be on the calculations that we do today. And I think all the questions are calculation questions. So I have already posted a video doing the PowerPoint calculations. So I'm not going to do those during lecture. We're going to focus on other types, just so you have a wider array. So now this time, notice we're doing a polyatomic, okay, PO4 phosphate, I believe. And you're going to do it the same way. Label each element present. Okay, you're not keeping the polyatomic together this time. So we have manganese, Mn. We have phosphorus, P. We have oxygen, O. So for the number of atoms, the manganese part, that's easy, 3. It's the polyatomic that gets a little funky because we have parentheses and then we have a 4 on the outside. So what that's saying is there are 4 PO4 molecules. So what you need to do is you need to take this 4 and put it inside the parentheses. So to figure out how many phosphorus atoms, you're taking that number outside of the parentheses and multiplying it by the subscript. So in this case, phosphorus, the subscript on phosphorus is 1. So 4 times 1 tells me there's 4 total phosphorus atoms. For oxygen, you're doing the same thing. You're taking the number outside of the parentheses and multiplying it by the subscript on oxygen. So 4 times 4 tells me there's a total of 16 atoms. So this is going to be a very large molar mass. Now we look up the molar masses. What is manganese?
Phosphorus is 30.96. And oxygen is 16.02.
So, very large. So I think we're kind of figuring out the method. I want to show one more, just because slightly different version of a chemical formula. You would have seen it if you've done the hydrate lab already. So it's how to calculate the molar mass of a hydrate. So let's do barium chloride dihydrate. This is one that we actually had on the lab. Just so we can see what the difference is here. So if we're calculating the molar mass of this guy, you still do the same thing. You make a list. The only difference is it looks different, but the way we approach it's the same. We have barium, we have chlorine, then over here we have hydrogen and oxygen. That's what makes up water. So for the barium, no subscript, so just one of them. For the chlorine, 2. Now for the hydrogens, we have to take into account this coefficient. It's the same way that we did it when there was parentheses and a number after the parentheses. So we're going to take this coefficient and we're going to multiply it by the subscript of each element in that molecule. So to forget the hydrogens, we do 2 times the subscript after hydrogen, 2. So 2 times 2 tells me there's a total of 4 hydrogens. Oxygen, there is no subscript, so we assume there's just 1. 2 times 1 tells me there's 2 oxygens. Then we look up their molar masses. If you do this long enough, you actually memorize quite a few. I don't know barium.
137.3.
Sorry, I didn't know. 137.3 is what we said. And I have a practice worksheet with answers on calculating these as well, if you want more practice. 70.90. What's 4 times 8? My brain's not working today. 32. Add them all together. Could possibly be, but we only need 1 decimal place this time if we're worried about sig figs, but I'm not really concerned about that.
I got 244.232.
240.
4.232.
Okay. I'm going to round it to just 0.2. With 1 decimal place there. Grams per mole. So the reason I rounded it, when you're adding, remember we look at decimal places for sig figs. And barium just had 1 decimal place, so our answer should just go out 1 decimal place. So that's why I rounded it. I'm not hugely concerned about sig figs when you're doing these calculations. I just happen to find it to make sure the sig figs are correct. So we've looked at pretty much every type of compound that you'll have to calculate the molar mass for. So what I want to do now is we're going to take these molar masses that we calculated and we're going to use them in convergence. Okay, and we're going to start with just single atoms, and then we'll move on to the compounds that we just saw now. So now I'm going to erase this calculating molar mass because we're not going to do that. Now we're going to do gram, mole, and particle convergence. So, we've done gram conversions before, going between different masses, pounds, ounces, grams, kilograms, all that. Now we're talking about moles and particles. So we're getting on an atomic level. What is a mole? So a mole is, it's actually the SI unit in chemistry to calculate the amount of something. So 1 mole is defined by Avogadro's number. Let me write Avogadro's number here. Avogadro. I'm not spelling his name wrong. Number. So Avogadro's number defines a mole because it says that 1 mole is equal to 6.022 times 10 to the 23rd particles. Notice, 6.022 times 10 to the 23rd. That's a positive exponent. So what that means is this is a ridiculously huge number. Okay, so why is this number so big? Well, when I use the word particles, we're going to see that particles means several different things. We can use this definition and apply it to atoms. And when we're applying it to atoms, that's when we're talking about an element. So particles can be atoms when we're referring to an element by itself. Particles can also be molecules. And when we use the word molecules in place of particles, we're talking about covalent compounds. We can also replace the word particles and use formula units. So this is a new term for us. And formula units is when it's an ionic compound. And this is going to be really useful for lab 8 because when you have to put the units, you're going to have to look at the molecule or the compound that you're calculating or doing conversions for and label it accordingly. So if, for instance, you're doing a calculation and you're doing it with a covalent compound, you're going to label it or use the units of molecules. But if it's an ionic compound, you're going to make sure to use the units of formula units. So let's see how we're going to apply this. So an example would be if you had, should we do grams to moles first? I have several different ones. All right. Let's actually show you this first. So when we approach a problem, to get between grams and moles, so when we're doing this conversion, we're going to be using molar mass. So that's what MN means, molar mass. When we go between moles and particles, we're going to be using this conversion here. So notice, it's set apart by an equal sign, so it is a conversion factor. So to get between moles and particles, we're using Avogadro's number. So I'm going to put AM for Avogadro's number. So now that I have this up, now I'm going to put up an example. And it's going to be how many, and I tried to write them similar wording that you see on the homework. So how many iron atoms are present in 0.21 moles of iron metal. All right, so how do you solve this problem? A whole bunch of new words that we just learned, okay? We've never seen moles before, all sorts of weird stuff. So to figure out how to even start, look at what it's asking and what it's giving. So it's asking for atoms. And atoms, we just said, is a particle. So it's asking you to solve for particles. What it's giving you is the moles. So you're doing just this step here. You're starting at moles, 0.21, and you're going to particles. So to do that, you're going to use the conversion factor up there. It's not giving you a conversion factor. You have to figure out what conversion factor to use. So what I'm doing is I'm starting with 0.21 moles, and I'm going to atoms. And to do that, I'm using Avogadro's number. Okay, so that's my plan. And the reason I'm writing in the plan for just one step is these are going to get complicated, and it's going to be several steps once we get further on in the chapter. So it's good to just kind of get in the habit of saying, okay, where am I starting and where do I need to go? So we're still doing the railroad tracks. Avogadro's number is our conversion factor. I'm going to write atoms here, since it's an element by itself. So when I do my railroad tracks, it's just like before. I start with what was given in the question, the 0.21 moles. That goes in my upper right-hand corner. And since this is my conversion factor, same thing. I'm going to place it here. I want to make sure to cancel out my moles. So the 1 mole portion is supposed to go in the denominator, opposite sides of the horizontal line so that they cancel. That makes the 6.022 times 10 to the 23rd go up top. So I'm going to multiply this out. It's going to be a very big number because what we're asking is how many atoms are present in this sample that we have. And atoms are very tiny. So we're going to have millions of atoms in that small sample. So you want to make sure to include
1.26 times 10 to the 23rd.
Times 10 to the 23rd. So including this times 10 to the 23rd is very important. Because if you don't include it, you're saying, I have just 1.2 atoms. Okay? No, you don't have 1.2 atoms. You have billions of atoms. So make sure you're including that. Now, we are still looking at significant figures. So to change this, or to round this to the correct amount of sig figs, you're looking at just the number in the original question. There are 2, so we want just 2. Exactly. It'll change to 1.3. We have to round up. And the units on it are going to be atoms because notice, that's the only unit that didn't cancel. All right, so now I'm going to write a question. When I read it in the homework, the wording of it confused me, but it's really actually very simple to solve. You actually don't have to do anything to solve it, but look at the periodic table, but it makes you think you have to do a whole bunch of confusing steps. So here's the wording that it said. It said calculate the mass in grams of Avogadro's number of sodium atoms. When I looked at this, I was like, huh? How do you solve it? First, I'll say the shortcut way to solve it. It's really very simple. What it's asking for, it's asking what is the molar mass of sodium? That's it. You can look at the periodic table and see, let's see, sodium is 22.99. So my answer for this would be 22.99 grams or grams per mole, depending what units they give you on the homework. So that's the answer. Why are they asking it this way? Because they're trying to get you to realize the definition of Avogadro's number. So when they say, if you have Avogadro's number of sodium atoms, they're saying, if you have 6.022 times 10 to the 23rd atoms, how many grams of sodium do you have? Okay, so this is what you're starting with. So if you were to do this a complicated way, do it with calculations, this is what you start your railroad tracks with. Okay? Now they want you to get all the way to mass. So they're giving you atoms, they're starting you here at the end, and they want you to go to moles, and then they want you to go to grams. So it's a two-step process. So we're starting at atoms, they want us to go to moles, and then they want us to go to grams. So this first step, you're still using Avogadro's number. Okay? Even though you're going backwards, you're still using the same information. You're just using it in a different way. You're going to be dividing instead of multiplying, for instance. So Avogadro's number here for this step is going to be the molar mass. So I need both of those pieces of information. So I have Avogadro's number And then for the molar mass portion, that's sodium. You look at what element or compound are they asking me to solve for. In this case, it's sodium. So to figure out the molar mass of sodium, I go look at the periodic table. The periodic table gives me that 22.99. So what that looks like as a conversion factor is 22.99 grams. And since it says per mole, that means that's equal to 1 mole. All right, so these are the two conversion factors I'm going to use when I do my railroad tracks. And once we do it all out, you're going to see that this is the answer. So, starting with what they gave us, they said you have Avogadro's number of atoms. So we have 6.022 times 10 to the 23rd atoms. So I'm here. I want to get to moles, so I'm going to use Avogadro's number to get there. So what I'm doing is I want the atoms on the bottom to cancel out the atoms I have up here. And then I'll have my 1 mole on top. So atoms cancel, but notice, same number as well. So the number itself cancels. So right now I have 1 mole. But they want me to get grams. They're asking for mass. So that's where the molar mass comes into play, putting the moles on the bottom. And the grams, 22.99 on top. Giving me, that is my answer. Okay? So I wanted to show you why that's the answer, but to also let you know if you see this wording, they're really just asking for the molar mass. So you don't have to go through these steps. So let's try one where you have to go through steps. That I wrote a few down. We did atoms from moles, so let's do mass now. So calculate the mass of 1.47 moles of oxygen. All right, so figure out what they're giving you and where you're going. So they're giving me moles. They want me to go to mass, and mass is grams. Okay, so we're going from moles to grams. This is just one step, that's it. So I'm going to start with my moles, and I'm going to go to grams. To do that step, we're using molar mass. So molar mass of what? That's when you keep reading and see what atom, what molecule are they asking me to solve for, and they're saying oxygen. So since molar mass is my conversion factor, I need to find the molar mass of oxygen so that I can do the conversion. So molar mass of oxygen, 16.00, and that's grams per mole. So my conversion factor would be 16.00 grams is equal to 1 mole. So now that I have my conversion factor, I can set up my railroad tracks. I start with the number given in the original question, the 1.47 moles. I then use my conversion factor to cancel out the moles and get my answer in grams. So what's going to go on the bottom, the moles or the grams? The moles. We're canceling it out. They have to be on opposite sides of that horizontal line. I'm going to get 16 grams on top. So remember, multiply across, divide what's on the bottom. So 1.47 times 16 will give me 2 and sig figs. We have 3. So what this is saying is if you needed 1.47 moles of oxygen atoms and you had to go weigh that out on a scale, you would put oxygen atoms on there, which you couldn't physically do because it's a gas, but if you could, you would put oxygen atoms on the scale until the scale read 23.5. So that's what these conversions, these calculations are useful for, is chemists use them on a daily basis so that they can figure out how much to use in a reaction, how many grams to use in a reaction. All right, let's try a harder one. So we've only done kind of one-step ones. So let's go from grams all the way to atoms. So we're doing the whole process. And we're going to do it with potassium. So if you have 0.69 grams of potassium, calculate the atoms. All right, so we have grams, we're going to atoms. So two steps, right? We have to go from grams to moles first, and then from moles to particles. In this case, since it's an element, right? Element, we're looking at atoms. So my plan: grams to moles, moles to atoms. What do I need? First step, grams to moles, I need molar mass. To go from moles to atoms, I need Avogadro's number. So let's get those listed over here so we can start our roto tracks. So to go from grams to moles, I need molar mass. Molar mass of what? Potassium. 39.10. So potassium is 39.10 grams per mole. So grams equal to 1 mole. So there's conversion factor number 1, my molar mass. Now Avogadro's number we have up there.
6.022 times 10.
In this case, particles becomes atoms because we're talking about an element. So I have my two conversion factors. Now I can start my railroad tracks. So I start with what's given in the question. It's going to be a big one. 0.69 grams. Next, I use my molar mass to go from grams to moles. 1 mole at the top this time, yep. And grams on the bottom. Opposite sides of the horizontal line, our grams are canceling. So if I stopped here and did this division, I would have the moles. But I'm going to keep going to get the atoms. So I'm using Avogadro's number to get there. 1 mole at the bottom to cancel, and then 6.022 times 10 to the 23rd atoms in this case on the top. So moles and moles cancel. So when we calculate this, you multiply across and divide by what's on the bottom. You have 0.69 times 6.022 times 10 to the 23rd on the top, and then 39.10 on the bottom. It's going to be a big number.
1.097647059 times 10 to the
22nd. Okay, so sig figs. 2. So I'm going to round that up to 1.1, right? 1.1. So what this is saying, if I measured out 0.69 grams of potassium on the scale, by doing this calculation, I can figure out exactly how many atoms of potassium I have, which is actually pretty cool. Because otherwise, the only other way to figure that out would be to get a high-powered microscope and count them, and no one wants to count that high. Something's going to be messed up along the way. All right, so we've just looked at elements so far. I'm going to do one more with an element, but then we're going to bring in compounds, which is going to get a little bit more complicated. I saw one like this on my homework, and I thought it was kind of cool. 2 million gold atoms you how many moles. So this one looks difficult because of the big number, but it's really not. It's the same steps. So what are they giving you? They're giving you 2 million, and they're giving you atoms. So we're at particles. They're asking for how many moles. So it's just one step. The tricky part is that big number. So you need to take that 2 million and put it in as an actual number. So what is 2 million? It's got 1, 2, 3, 4, 5, 6 zeros. So this is my 2 million atoms. I'm going to convert that to moles, and I'm going to use Avogadro's number to do it. Okay, so I'm going to write Avogadro's number over here. That's my conversion factor. And since this 2 million is the number they gave me, that's what I'm starting my robotracks with. And then it's one step, so I just have this one conversion factor to get there. I'm going to put my mole on top, because that's what it's asking for. And then Avogadro's number on the bottom.
So would that be 2 times 10 to the 6 or 7?
I have to count 6. So you're asking scientific notation, it would be 2 times 10 to the 6th is the same as writing 2 million. So you're taking that and dividing it by 6.022 times 10 to the 23rd. So it's going to be a very, very small number.
6 times 10 to the negative 18.
So I just stopped at 3 because there's just one sig fig in the question. So let's, 10 minutes we have left, try a harder one. So we've only looked at elements by themselves. Now we're going to look at, well, what if we're trying to figure out compounds? So molecules, formula units, those types of questions. Figure those out. Let's see what I have here. Oh, great, I didn't write down an example. So I get to make one up. So let's calculate mass in grams. 3.7 moles. All right. So what are they asking for? Grams. What are they giving us? Moles. All right, so this is still just one step. We're starting at moles, that's what they're giving us. We're going to grams. To go between moles and grams, what do we need? Molar mass. But this time, since it's not an element by itself, we have to calculate the molar mass. So we have to take this formula, CO2, over here, and I'm going to calculate what the molar mass of CO2 is by making that list. So this is what we did at the beginning of class. We have carbon, we have oxygen. Atoms of each, molar mass of each. So how many atoms of carbon? 1. How many atoms of oxygen? 2. The mass of carbon, we look at the periodic table, 12.01. Oxygen is 16. So we get 12.01 plus 32.
44.5.
And then the units are grams per mole. So this turns into a conversion factor for us by setting it apart with an equal sign. So this is what we're going to use as our conversion factor. Now, we can do our robotracks because it's just one step and we have the one conversion factor we need for the one step. What do we start our railroad tracks with?
3.70.
3.7. We'll use this calculated molar mass to get rid of our moles. We're looking at 3 sig figs for the answer because we had 3 in our original number.